this one too. But when I took it to my mentor, Dr. Roble, downstairs, I said, hey, I had this great question Friday and I couldn't answer it. He goes, well, why are you doing lambda in the film? He goes, because of course it makes sense to it. No wonder. This looks like lambda in the air to me. I went, oh, yeah, you're right. But we've got to use the index of refraction of the film due to the time that it takes and a few other things that we don't go into. But when you see the formula, you go, okay, now it all makes sense. All right, so now, how many phase shifts, and we're going to do a quiz on this here in a minute, okay? So how many phase shifts, okay, when it comes here to here, what do I have a phase shift? Yes, because it's going from greater to higher, so that'll be a 180. So 1 equals 180. What about at this boundary? So we look at these two boundaries. What about this boundary from here to here? Is there a phase shift? No. Okay, no. So here's the rule. If you have for a 180 phase shift, for a 180 phase shift, here's your two things. Here are your two formulas. 2t times n, 2t, now t is the thickness of the thing because it goes back and forth. 2t times the index of refraction in here of the film. Let me put n of the film here so we don't get confused. It's real simple. Equals m plus 1/2 times lambda. Okay? Times lambda. And that's lambda in the air. So now it makes physical sense to us. All right? There you go. That is for a maximum. Okay, now this is fancy physics talk. For a maximum, what did we call a maximum on Friday? What kind of interference? Constructive or destructive? Maximum interference. It's really bright. There we go. This is what is known as constructive interference. I can see it. Constructive. I can see it. Okay? Now, if I have 2t times n equals m times lambda, oh, by the way, what does the m equal? 0, 1, 2, 3, depending. And so that's how we find, in other words, for me to see this thing, that thickness has to be an integral multiple, m, of constructive interference. All right? So there we go. All right, now. Okay, now, 2t times m gives me a minimum. What do we mean by minimum? Destructive interference. I can't see it. Destructive interference. Okay. All right. Now then, let's look at a different case. Let's look at one other case. Then I'll slap your quiz up there so by the time you get done with the quiz, you'll be an expert. And we'll go over it. We'll go over the quiz. But I want you to work together because I want you to get this. Because this is kind of, and this comes out, for those of you, for the 4 of you that were here on Friday. No, actually it wasn't a bad turnout for an Orgo test day. But anyway, oh, and this one, m is equal to 0, 1, 2, 3. This probably makes a lot more sense than what all that stuff we were doing before. Okay, so now let's take a look at this. Now, one of the things that they like to do is we like to put a thin film on the lenses of cameras, binoculars, those kinds of things, so that the light transmitted through has minimum reflection back. In other words, if you've ever noticed, if you look at somebody's binocular when they're looking at binoculars, you see nothing but black for the most part. When you're looking at when somebody's looking through binoculars or something, all you see is black. You can't see anything because, especially a really, really high quality set or a high quality camera, because they want most of the light. They don't want this to happen. They want all destructive interference to take place. Okay, so here we go. So tell me what this phase shift would be. Let's say we've got n equals 1.00 right here. N equals 1.38 for the thin film. Now that's my film. The one in the middle is the film. And then I've got n equals 1.42. And I'm just making up those indexes of refraction. I probably should have looked up some real ones. All right, so here we go. We're coming from here. Here's my first reflection. And here's my second reflection. Coming out like this. All right. What's my phase change as I go from here to here? From here to here? 180. So I'm just going to say 180. What's my phase change as at this boundary? 180. What's 180 plus 180? For degree purposes, is there any difference between 0 and 360? No. So there's no phase change for this one. None. No phase change. Same as 0. Unless, of course, you're doing small pipe snowboarding or something, then there's a big difference between a 360 and a 0, but that's okay. We're not doing small pipe snowboarding. All right? We're just doing some simple optics. Well, not simple. We're just doing some optics here. So in this case, guess what happens? These guys are flip-flopped. All right? So when we have, so for 0 or 180 or 360, in other words, you've got this. For m equals 0, 1, 2, 3. Well, that was silly. Wait right there. But anyway, for m equals 0, 1, 2, 3, you have this for the maximum. The maximum will be 2tn equals m times lambda. And that lambda is the lambda in a vacuum or lambda in air. Okay? This is your maximum. And maximum means what? There we go. Constructive interference. All right. So we can see it. Oh, Tingy, can you hear me? Okay. All right. And then for m equals 0, 1, 2, 3, we've got 2t times n. And this is so we can find the thickness of the thing so we can actually see this stuff. Is it going to be constructive or destructive interference? And in other words, when we're making this film, we know what the spectrum for light is, for the certain lights that we want to see. And so let me set this up. The one thing that was a little bit embarrassing, well, not embarrassing, but just kind of different. So now, when you have this kind of arrangement, when you have 0 or a 180 phase, or a 360, 0 or 360, then notice your equations flip-flop for the maximum and the minimum. Okay? All right, now then, here we go. I spent hours working this. Actually, I spent 12 minutes working this up. But anyway, here you go. Here comes your quiz. Now, it's what I'd really like for you to do. What I'd really like for you to do is to write this down, copy it, and not turn it in, but just give me your blank sheet with your name on it so that I can give you credit for the quiz, because we're going to go over this. There's no grading it. But I want to make sure that I want you to go through the process, and I also want you to get credit for it. So basically, at the end of the hour, give me your name with a... What's that? Sure, why not? All right. So in other words, so that kind of boils down to, do you have to do this? No. but I want you to. And I think, all right, so you got this down? And thank you for your question. That was a great question. It left me mulling all weekend. Then I saw Dr. Robel, and he said, well, break out your, I forgot. The weird thing that I found, I went to my old physics book that I had in 1979 when I went to Mizzou. And, yeah, I was looking through it. It's starting to fall apart. But the weird thing was, when we do really small measurements, when you guys have been doing your wavelengths, what have they been showing up as? What unit do they assign it normally? Nanometers. Yeah, you've been doing it in nanometers. Guess what it was in my textbook? Angstroms is what they're using. They're using angstroms. And the reason was these textbooks were written, my textbook in 79 was probably written mid-50s. By the time it got approved, and then it went through all its, because I was using the 5th edition. And in fact, a lot of the textbooks that we're using now, the head authors are dead, but they live on forever in new editions of textbooks. But anyway, and with changes, and so mine was in angstroms. And the reason they've gone to nanometers is because nanoseconds and is all computing stuff. Back in the 40s, 50s, and 60s, all this computing, this high-speed computing things with nanoseconds, that was kind of unheard of. But we got it all straightened out there? Okay. All right. All right, so here you go. Here's 4 questions. Here's 4 questions. Questions 1 and 2 are going to look real familiar. All right, so here you go. Let me, there you go. Now what I want you to do is, I want you to tell me what the phase shift is going to be. Is it going to be 180, 360? Figure out what the phase shift is, and then write down what the 2 equations are going to be for constructive and destructive interference. So you've got 3 things to do on each problem, okay? In fact, this would be a great kind of test question, sort of. What? What I want you to do is I want you to write down what the phase shift is and what the 2 equations would be for constructive or destructive interference. All right, so this is for question 1, which we did. That should be in your notes. Here's for question 2. Here's for question 3. There you go. So this, I think this makes it a lot simpler than what we were doing before. Lot simpler. What's that? If it's destructive, it has a, oh, you can see it or not. Now then, so it's maximum or minimum. The maximum equation is constructive. The minimum equation is destructive. Okay, right here. Let's try it one more time. Here you go. And that's fine. This is good. In other words, this equation gives you the is for maximum interference. All right? And this is for when the phase shift is 180. Yeah, what is the, no, on a test you'd get, I can see this light that's 600 nanometers. Okay, I can actually see it. So that means there's what? Constructive interference. And here's the situation. It's a soap bubble. All right? And here's the situation. It's a soap bubble. How thick is the soap bubble? Minimum thickness of the soap bubble. That's what. So do you understand now what we're doing? Yeah. Yeah. Okay, let me put the... No, you can't tell whether it's constructive or destructive just by looking at it. You've got to write down either the destructive equation and the constructive equation. There's 2 equations. There you go. Yeah. I see what you were trying to do. You were trying to solve something. There's nothing to solve here. Okay. Right. I just want you to get in the I just want it to get programmed into your brain what thin film interference is. And because I can always tell my students, I can always tell people that my students know about thin film interference, which kicks most people's butts because it is confusing. Problem number 4 is just like the one we did. I mean, it should be in your notes. 1 and 4 should actually be in your notes. 2 and 3 are the only 2 that are kind of different. I know what I can do. What's that? Did you wind up with the same phase shift? There we go. Okay. Situation 2 would be something like if you have that thermopane glass type stuff where you got the glass and you got the thin film between it, the air between them. This is more your classic case of air, oil, and water. Oil on water type thing. Oil's less dense, but that's, see, this is what material science guys and those guys downstairs look at. They go, okay, if oil is less dense, why is its index of refraction greater? And all that kind of stuff. We don't know. It's due to, I always say when students ask too hard of a question, quantum effects. And then you can move on. Yeah, that's my answer to everything. Quantum effects. Yeah. Just take quantum mechanics. There you go. Oh, no, well, here's, it reflects here and here. Yeah, yeah. Oh, yeah. Oh, no. We're not doing one more reflection. Yeah, right. No, we just look at the thin film. It's not a thin hot toddy, interference here where you'd have cream, rum, coffee. We're not doing that. Thin Irish whiskey interference. No, we're not going to do that. Yes, read. What's that? If it goes from low to high, there's 180. Low to high. So from here to here is a low to high. From here to here is low to high. And so that would be a 180. From here to here, 0. What's that? Reed's question is a good question. See, this is why physics questions have to be well vetted before you put them on a test. Because his question is, well, do I have to put the 2 down, 1 and 2? My intent, which I didn't tell you, was add the 2 together. You're going to have what happens here and what happens here, and then add those 2 together. Some of them are going to be 180 and 0. Some of them will be 180 and 180, which comes out to be just like 0. And then some will be 0, 180, which is 180. So clear as mud, which they wanted it up. Oh, all right. Boy, it's a nice day. I'm telling you, graduate school, UC San Diego, I'm telling you, every single day it's like this. Every day. It almost gets boring. The weather forecasts in San Diego are hysterical because it's the same thing every single, except that what do they give you? What's the most important thing they give you in San Diego for weather? There you go. Surf report. That's the biggest thing. So out of the La Jolla Coves, you've got the maximum waves of 6 feet. Okay, we got it? Everybody get it? Okay. let's just go through this so we make sure we've got it. To make sure. Okay, so on this first one, we did this one. We basically did this one in class. So 1 is a 180, and 2 is a 0. So the total phase shift was 180, and then since it would be, it'd be these guys. It'd be these two. This is your constructive equation. Here's your destructive interference equation. All right. Question 2. This is like and they do a lot. Oh, to test materials. Some of you rock jocks, you guys do this all the time too. You put like films between two things, and you check the spectroscopy of the thing. Use oil. Yep. Okay. So that's more like down here. All right. Well, actually, what you're doing is here, you're putting oil in the middle between air and air, right? Type thing. Oh, okay. Oh, I see. So it's actually more like this one. Yeah. Oh, and depending on the phase shift, that gives you your index of refraction, and then you figure out what it is. Right. Cool. All right. So anyway, so what's for number 2? It's just like number 1, right? It's no different, except that this was 0 and this one was 180. But then it gave you the same thing. What about number 3? This is more like oil on water. You've got a phase shift of 1. What about here? Right here, no phase shift. So it's just a 180 also. Yes, Jordan. Number 2. Okay, it goes from high to low, 0 for this guy. Low to high, 180 for this guy. Okay? Good. Good question. All right. So this one, low to high, so there's a 180. What about this one? Yeah, 0. Okay, then last but not least, this is what we do for, so 1, 2, and 3 were all identical, right? It should have been about the same thing. All right, now for number 4, we've got, this would be a 180, and this would be a 180, so what's that come out to be? A 0 or a 360, so therefore your equation should look like these guys, right here. For 0 or 360, then it comes out this way. This is always, besides magnetism in general, this is always kind of the trickiest thing in 220 that you run into. But I'm glad I got challenged on it so I could teach it better. Yes? Oh, you decide. You decide. Okay, if it says, Ben had a good question, and it helps you when you're actually solving the problems. If it asks for a minimum thickness, in other words, what's the minimum thickness that will give me constructive interference for this kind of situation? I don't think I'd want M to be 0, because that's just 0 on 0. That doesn't do anything. So M would be 1. Usually you just pick M to be 1. Sometimes it has to be, so right here for the minimum thickness, it'd be M equals 0. Okay? And for the, what's the M stand for? That's just the integral multiple for your phase shifts. It's just 0, 1, 2, 3. Waves work in a funny way. They just work out as 1, 2, 3. In other words, you can multiply the lengths by 0, 1, 2, 3, 4. For certain, in other words, for certain wavelength, for certain colors, there's certain thicknesses where I could see it. And those are going to be in integral multiples of that wavelength, is what we're saying. Okay? So this thickness can change all the time, but at certain certain wavelengths give off certain spectra of light and all that kind of stuff. Okay. Yeah. Which value for N? Oh, excellent question. What is the value for N that we put in there? For the one that matters, which is the one in the middle, the film, the end of the film. Okay? See, that's why, good. So the N that matters is this guy. Here's the N that matters in your equation. Good. Good. Okay. All right, now then. So hang on to that for your notes, because that'll be good for cheat sheet transfer and all that kind of stuff when you take the test. 8 o'clock Thursday morning. It'd probably be a nicer day than this even. Won't that be fun? Anyway. But like I said, I will bring extra copies to my 210 class, which is on Tuesday, if you want to take it then. What's that? Yeah. Yeah, we can do that. The main one's here. Okay, let's go on to the next thing. Computer. Oh, I haven't even logged in yet. Contemplate life for a minute. Okay, one of the things, all right, the next thing we're going to talk about is polarization, which is kind of cool stuff, all right? You all can't see, whoa, all right, glad we're not showing a video. That would have been kind of loud, but anyway, we go down. So what we're going to look at is polarization of light, and that's the amount of intensity that goes through certain materials polarize the light. So let me call up the slides, otherwise I'll get you all confused before we even get started. Now this is actually not too hard. It's much easier than thin film interference. I'll tell you that. What chapter are we on? 24? 24. Okay. 25 we will probably, I'm not going to lecture on 25, but on Friday we'll go over some of the homework problems. They're all, when's that homework due? It's due Friday. Monday? Oh, cool. Then we can look at it Friday then. Okay? In other words, what I want you to do on chapter 25, all chapter 25 is dealing with is telescopes, the human eye, telescopes and microscopes, and this kind of shows you the basic equation and how those things work. It's kind of a self-study thing. Okay? And all the problems that I gave you are the ones that have the hints that'll just walk you through it, how to do it. So you should be okay. But we'll look at a few of them on Friday. There's a view of your dorm room if you go to San Diego. All right, but anyway. All right, so that was painful. All right, so here's all the phase shift. Here's all the, notice, this thing, it's smashing down, or the thickness of the film is different here than it is here. Okay, and so that's why you got different colors coming out. There's some are being destructed, some are being constructed. And when I smash it, and you all have seen that because you all have worked with microscope slides. In fact, most of you all have forgotten more biology than I know. So, but anyway, but in your biology class, you know, when you actually smash down the slide, it kind of goes blank for you, so you can actually see what you're supposed to be looking at. Okay, so we've done all that, done all that. Oh, diffraction grading. That was what was next. Oh, I forgot about that. All right. Shoot. Darn. All right, diffraction grading, here it is. Moving on. Basically, what diffraction grading is you've all seen the back of a CD. When you move it around, it's got all those fancy colors and everything. That's because CDs, and due to the engineering capabilities that we have now, they were able to cut reflective. These weren't transmittive. Okay. 3 things. There's 3 things you need to know that a light wave does, all right, that it can do. Here it is. If you know nothing else, this is getting you to become better parents. So when your kids ask you, you can say, light does 3 things. It either reflects, it transmits, or it what? Refracts. There you go. So those are the 3 things. Now for a CD, what they have is they've got reflecting. So you've got this reflecting surface that's coming back, but it's cut into diffraction grating. And what diffraction grating does is it makes these bands more intense. so that it can read the data. So you can put these little notches along there, and so it can say, oh, that wavelength is this long, so therefore it's a 1. That wavelength is this long, so therefore it's a 0. And it reads those bits of data that way, so you get your sound, which is all in 1s and 0s. Okay? And the thing is, here's what's amazing to me, is they can put, how many slits do you think they can put on a, in 1 centimeter? 1,000? Good guess. Anybody else? Anybody else read the chapter? No. Okay. About 40,000. They can go up to 40,000 slits per centimeter. That's incredible engineering, I think. So, and really, if I kind of have a scientific hypothesis that the people 500 years ago were as smart as we are now. They just didn't have the engineering to do the things. And it just takes a while for engineering to catch up, you know, with new materials and stuff like that. Okay, yeah, probably smarter in some ways. However, what we're doing though now, if you think about it, 500-600 years, let's look at Western Europe. I'm getting on a philosophical thing, so I'm going to let you go. Because I forgot about diffraction grading. I'm stalling. All right, but anyway, so I forgot to prepare this part. I know about the whatever else we're supposed to do. Oh, polarization. I was all ready for polarization, and I saw this and went, oh. All right, but anyway, I think my theory of advances, especially in the recent 150 years, is because we're educating more people. Think about back in Galileo's day, is only who got to be educated? The rich white males. That's right. You got it. The rich white males, they're the only ones, or the ones that ran off to go join a monastery or something like that. Okay? So anyway, so because that's why it's so important that we educate everybody, because somebody else might have a bright idea that'll give us. All right, so anyway, double slit interference. What I would like for you to do, make sure your name got on something, all right? And I was going to, oh, there we go. Okay, here's the quiz, all right? If you all got, and that'll be good. We're way behind on the titles for Ting Yi, but that's okay. All right, yeah, you can go. It's